So extreme value theorem was 5.2. So I'm just going to back to that. There it is. So if f is continuous, then there's a max and a min on the interval. This is what that one said. It has at least one. So these kind of questions, we did one on Tuesday like it, but not, it was a different, did you get on and look at anything?
I did.
Okay.
Because the other one was just asking if you could use it.
Which is, yeah, that's kind of the same on this, excuse me, on this one. So which of the following is guaranteed, meaning can be used with the EBT?
It's asking which one is continuous, so that.
Yes. Okay. That's really the kind of hidden question behind it. And so for that, like, we don't have to graph it all. What do we look for? Like, how can we, thinking of this as a multiple choice, so it's, you know, it's quick time, how can we quickly assess whether it's continuous or not? Yeah, it's the same.
So, like, yeah.
Yep, so check where any issues would arise in the denominator. So, like this one, on the interval 0 to 2 pi, if sine of x is -1, we're in trouble. So does that ever happen? At pi, right? Not pi, sorry, at 3 pi over 2. Okay? So, at 3 pi over 2, sorry, I was pausing to think of the word. There we go. It's, the denominator is undefined. It's the whole thing. Anyway, what about this one? Is this ever going to be 0?
Is that an x or a pi?
It's x squared plus pi. I know, it never shows up very good, even if I make it bigger. Will that ever be, will that ever have a vertical asymptote? Is kind of what we're asking. So it's good. Of course, x minus pi, but we have this numerator, excuse me, but can we just look at, let me say that better. We could factor the numerator, potentially cancel x minus pi. But what?
But that still would continue to be
Yeah, I mean, it's going to have a hole right there, right? So, yes, Tuesday, Christian, we talked about the case where it's like something like this.
Yeah.
So the limit doesn't equal the function value. So we reviewed the definition of continuity. How about this one? Is the limit the same from both sides?
No.
No, because remember we have to split the absolute value. So this would be x minus pi over x minus pi, which is 1, the limit, like as we approach pi. Yeah, and then the negative version of the numerator. So that would be -1. Anyway, all that to say that this one's fine. So the extreme value theorem would guarantee it on that only. And again, it's really just a question of can we use it? So let's compare that one to the one we did on Tuesday. Just so you can see it, especially Christian. But this was a mean value theorem. So it can be applied to which one? Same kind of question. So looking for where the numerator or denominator is 0. Remember, for the mean value theorem, though, what else has to be true?
That is differentiable.
Yeah, it also has to be differentiable on the same interval. So continuous on a closed interval, differentiable on the open interval. So we ended up highlighting this one. On the interval -5 to 5, this denominator was okay. The rest of them, there was a point where it wasn't. Those are kind of subtle. I mean, once you see them a few times, you kind of know, but they can be kind of tricky if you don't think of it as it's really a denominator problem. Okay, so then we talked about Tuesday. Talked about intervals of increasing and decreasing. Big idea, I'll just catch you up, is find the critical points. So do you remember that part?
Yeah.
So the derivative is either 0 or undefined. So we found the critical points and created these little tables where we left space around each critical point to assess whether it's positive slope or negative slope on either side. Okay? How'd that go for you?
That was pretty good.
Any questions on it? Okay. And in terms of evaluation, you don't have to worry about the value, just if it's positive or negative. So like this one, our derivative was negative 2x minus 4. So anything up to negative 2 would make that positive, and then after negative 2 is negative. And again, we didn't have to worry about the value. Because like that one wasn't too bad. The one back here was a little bit more work with the squared derivative. So just to save time, more look at sign. The application, the big idea that came out of that is to read carefully. So let's read this one just to review. Can you see it okay? The rate of change of fruit flies in this kitchen is given by this function, and it's just r of t. But we have to know that even though there's not a prime, that it's actually a derivative function, right? It's already a rate. So show that the number of flies is decreasing. We wouldn't want to do r prime of 3, because then that would be the rate of change of the rate of change. We would be one step too far, right? That's why this is a reading, caution reading question, because you could even write it in here wrong. Like, so the number of flies is decreasing because if you said r prime is less than 0, you'd be on the double derivative. So that was the big idea there. How long are those problems taking you, roughly?
Some of them were like longer than those, but streams like 5 minutes, which is kind of a lot.
5 or 10 minutes?
Yeah.
Yeah, but it's also the first try too, like early on. And if it was something like this, where you had to create your own table, so I don't mean like this exact problem, but if you had to create a table that big, that would probably be an FRQ. So 5 or 10 minutes would be okay anyway. Okay? Where you're writing out the justification and stuff. In terms of justification, Christian, we had, let's see if I can find one. So you say the usual explanation, but then it was because the derivative is, but you can use the inequality symbols to justify it. So, all right. So no questions on that. Okay. So it's kind of our next section. I'd like to get through 2 sections today, if it seems to be going okay. It's going to look a lot like this. So that's kind of nice. It's going to be similar looking work. And we'll come back to these. I'll tell you about that in a little bit. So again, we'll find this first derivative, but now we're going to find the local extrema and actually use that to find their value. So just like yesterday, or Tuesday rather, we were, just a second ago, talking about where it was increasing or decreasing on either side of the derivative. This, we're going to just take that one step further to say, well, if it's increasing then decreasing, or decreasing then increasing. Well, and you could probably tell me already, honestly, with that.
If it's negative to positive,
It's going to be a what?
it's going to be increasing.
But we're trying to say, is it a minimum or maximum?
Oh, it's a minimum.
Yeah. Yeah, and then vice versa. If it's increasing to decreasing, it's a max. So we just do our table again, and then we'll be able to describe, is it a max or a minimum. So. Just as a quick, I don't want to scroll around, but as a quick preview, the next section will be how do we find absolute max and min, which is really just one step beyond this, and it's a little bit easier actually, which is kind of nice. So, first derivative test, start with something we know, so like a quadratic function, We've seen that 8 billion times. So we know that it's going to have just either one max or one minimum. And we already I just sketched it a second ago, but the slope of this is decreasing and then increasing, so we know that's going to be a minimum. How did we find if it had a max or a min before? You guys remember back in like pre-calc or algebra 2? Without having to graph it?
I don't remember. I remember talking about like the different shapes of the graphs, like with the different powers, like we would comment like with a 2, a 3, 4, and like how many times it would change.
Yeah.
I don't remember much else.
Okay. Well, specific with quadratics, remember it's just the sign of a, the number out front of x squared.
Yeah.
So if a is positive, like this one, it opens up, so it has to have a minimum, right? And vice versa. So if it's specifically quadratic, you're good, just probably by doing it that way. But that's why it says something we know. All right, so C and D, we're going to use those to define critical points, critical numbers, so the x coordinates. So assume that we have done our derivative, set it equal to 0, and look for where it's either 0 or it does not exist. So there's a minimum. This is just where we're writing in words what we just saw. There's a minimum value at x equals c. How would you word that? Because why?
Because f of c is, or f prime of c is increased. Or like,
Oh, was it like what we were saying earlier? It's negative and it's positive.
Yeah. Yep. That's all.
Well, if it's a minimum.
Yeah. So for a minimum, it's negative and then positive. And then, of course, just the opposite. So f prime of x is positive and negative. Implying that it's on either side of the critical point. Okay. All right. We were talking about this the other day. You have to be good at taking derivatives, right? So we kind of reviewed some of the rules. Why don't you try taking the derivative of that, just as a quick review. And then we'll go from there, but go ahead and do your derivative. Okay, how about 2 to infinity? Well, we have positive, and then anything bigger than 2, this is going to be positive as well. So, positive. Okay, so you could, if you want, you could kind of sketch a little diagram. So slope is negative, and then positive. So at 2, we have a what? Or at negative 2, excuse me. We have a local minimum. Then we have positive 0 slope. And another, sorry, I did that wrong. Okay, and then it's down, so what's that one going to be? Max, and then back to a minimum. Okay? Obviously the highlighted longer pieces, that's just for visual, if you don't want to write that. So how would we describe this? F of x, and put a prime, f of x has a what? Yeah, and I'm going to write the word local in there. There's 2 of them, so at x equals negative 2 and x equals 2. Because, here's how we say this, and we could go change this if you want to match so you see it more often. But we can say because f prime changes sign is the phrase that we use. and in this case from negative to positive. Okay? And then for the max, we just reverse that. So, any questions on that? That feels like an FRQ, doesn't it? Yeah. Speaking of that, if it is an FRQ, you do need to show this, not just show your critical points and then state. So you'll need to show your analysis, your sign chart. All right. If H of C does not exist, X is equals C can't be a critical point. In other words, check the domain. Can you think of a case where that would happen? I mean, this one is going to, but like a description. I guess since I'm telling you, like, what kind of graph would this be, probably?
Would it be a line?
A straight line? Is that what you mean?
Yeah.
No. So it's one of those kind with a vertical asymptote, right? So if we find that we have a critical point on the vertical asymptote, but the vertical asymptote is not part of the domain. Okay, that's what we're going to find here. So how do you have to do, why don't you guys, again, practice doing the derivative on that one. Why don't you jump to the test prep section? There's two numbered problems. The second one is pretty long. And they're both really good ones. So let's take a little bit of time to work on them, and then we can check back in. And then maybe try to do 5, 5, 2. So what did you guys put on 15? A, C, and what? B? Okay. Well, we only had 2 that didn't get picked. All right, well, here's kind of how you should think of that one. So G is negative. That's kind of what this is telling us. And, excuse me, so F prime is some quadratic times a negative. So if we run through these, it'd probably be good to factor that. What do you get when you factor that? Yeah, like if we solve for the, let's say, zeros of F prime.
X minus 1.
Okay, let me write that first. So we get 4 and negative 3.
Oh, I flipped them.
So that kicks out these 2. I wouldn't necessarily kick this out yet, but all right. So then let's just kind of narrow it down between those 2. So in order to have a maximum at negative 3 and a minimum at negative 4, what has to be true? Let's just pick one of them. If it has a max at negative 3, it would have to go from positive to negative, around negative 3. Okay? So if we plug a negative number in here, let's say negative 4, so positive minus positive, well, plus positive, and then minus 12. Okay? So times negative, so that would be negative on the left side of negative 3. So that doesn't work, right? Because that would be, it would look like this. If we stick negative 3, it would look like this, was what we just found. Are you good on that?
Yeah, I just flipped. I didn't.
Okay.
I put negative 4 and 3 with that.
Okay. Anyway, so that kicks out negative 3 being a max. But it does kind of confirm a minimum. And then we can check the other one, right? At 4, like if we plug in a 5, for this to be a max, it would have to be, here's 4, it would have to be negative on the right side. So 5 squared minus 5 is 20, minus 12, that's still positive, but then times a negative. So B. Tricky little question, I think. Alright, this one, I totally could see this being like a whole FRQ. And it's kind of all over the place, in my opinion. You want to just work through it, or do you just want to ask questions, or what's best? I'm happy to work through it.
Yeah.
Just want to do that? Okay. Alright, so we're given quite a bit of information in the text. So this is important. So F, it's kind of tucked in there. F of 1 is negative 2. That will show up at some point probably. And then we're given F prime. That's important to remember and read carefully what we're told. That it's prime. Okay, and then we can kind of see this, but it tells us that it actually is going through at 0 and negative 2, or negative 2, 0, 2, 0. And then we have a horizontal tangent at x equals negative 1, so telling us that that's a max. Anyway, so we have this e to the f of x function. So it says write an equation for the line tangent to the graph of g at x equals 1. So what do we need? What do we need to do that? Okay, so we need g prime of x equals e to the f of x times f prime of x. So that's our slope. And then for our equation, what else do we need that we don't have directly? Yeah. So x1 is just 1. y1 is e to the f of 1, which we were told is negative 2. Okay. So we can plug all that. Oh, well, I guess we actually need a value here too. Did you say that?
Oh, no.
It's 3 because you given that point of the graph.
It's not 3. You're talking about the derivative?
Yeah. That's it.
Because we have this e to the f of x.
Oh, because your f prime of x is 3.
Yeah.
Okay.
I need to, I'll just write it up here. So slope at x equals 1. So we get e to the f of 1. Let me just write it so I don't have room to write it out multiple times. So 1 over e squared, there we go. And then f prime of 1 is 3, like Aiden said. So I'll just stick a 3 right there. Everybody good with that? Okay. Anyway, with all that, we get y minus 1 over e squared equals 3 over e squared x minus 1. So kind of an ugly equation, but it's okay. How'd that one go?
I didn't take the derivative of g of x, right?
Okay. All right, average rate of change of g prime, the derivative of g over this interval. Okay. So we're taking the average rate of change of this guy. What is average rate of change?
X
Like-
plus minus x.
Yeah. Oh, and by the way, I did look it up. We should write AROC to be specific about an average rate of change because arc, like I was saying that they could be arctan, arc cosine, those kind of things, but also it talks about the length, like if we wanted to find the length of that arc of that curve, and so we don't want to get mixed up there. We'll do that with integrals, antiderivatives down the road. You look like that's still not what you were thinking.
I don't know.
Do you have your stuff from back then?
Yeah.
Maybe you could look at that first.
Yeah, that whole.
Okay. So we want to go g prime of 2 minus g prime of negative 2 over negative 2 minus 2. So it gets a little ugly, right, with this?
You would either have to have your
Yeah, I have it
your
backwards.
2 or your, you have to put your calc.
I just wrote the denominator as, there we go. Okay, so we're plugging all that stuff in here, right? And that's kind of a mess. So we have e to the f of 2 times f prime of 2 minus e to the f of negative 2 times f prime of negative 2 all over 4. Okay, so it looks bad, right? At least I think so. Because, number one, we don't have f of 2. So when you don't have it, look deeper. What is f prime of 2? It's 0. F prime of negative 2 is also 0. So that kind of saves the day. Because it all becomes just 0. Okay? Good on that one? Alright, on our interval, find all x values where g has a local minimum. How?
G prime of negative 2.
And doing what with it?
Find your local extreme. Which is 2, negative 2, and 4. You gotta find this. Let's see, this is where it goes.
Yeah. Okay, so g prime has this f prime in it, so this is what you were saying, I think, Aiden, right? So where f prime is 0 is negative 2 and positive 2. Does it ever not exist?
Yeah, at negative 4.
Oh, yeah, because it says that there's a
So what's the whole tangent?
Or tangent.
Alright, you lost me. Sorry.
It's because it says that there's a horizontal tangent at x. Yeah.
Okay, but why are you saying that that doesn't exist then?
It does exist. There's a y value for.
Yeah. A horizontal tangent is not.
F double
Oh,
prime
then
is-
maybe I was just thinking of like. I was thinking of like, I don't know, like massive tangent. But I
Okay.
don't know how that would make sense.
Okay.
Yeah,
Okay. Okay. So I'm thinking of this e function. This is always positive, right? And it's not going to not exist unless we're left of our interval. And then, of course, f prime, it looks like it's fine. Okay, so how are we going to figure out if it has a local minimum? The what? The table, yeah. Just a sine table. So what's our slope? 0 there. So again, e to the f of x is always positive. So it's really determined by f prime. So left of negative 2, or huh?
Negative.
Yep. Sorry, I didn't hear you. I didn't want to cut you off. Okay, in between the two, positive. And then negative again. Okay, so local minima. Tell me what's going on, like, so if we do our little picture, it's negative and then positive, and then negative. So, how would we justify?
Because G of X has a local minimum and X is distinct by 2, because G prime of X changes sign.
Good.
But, yeah.
But we have to say specifically from changes sign from negative to positive. Okay. Is that helping? Where you guys got stuck on that one, right?
Well, I messed up the
Yeah,
derivative.
well, it's because I messed up the first one, since I didn't.
Oh, like
So everything-
everything after.
Everything after that.
Which was confusing. Well, okay, because I was kind of, I kind of thought that G prime of X would just be e to the f of X.
That's why.
And so I was on C and I was like, wait, but it's never negative. So how can there be a local minimum if it will never be negative?
Yeah. Well, I mean, you were thinking good. Your thinking was sound after the derivative issue. Anyway, this one, how do you think you do that one? I don't know if you got to
I
it.
just went through and plugged.
Yeah, just plug in there,
Everything
negative.
was positive and negative.
Yeah. What'd you end up with?
So positive.
Positive? I don't know what I got. Positive, yeah, same thing. Okay. What could we say about on this one? It just says where it has a local minimum, but what else could we say about that point?
So local X, local X.
Yeah. Okay. All right. Well, how are you feeling about local extrema? Okay. Okay. We have time to do 5-5. Are you good with that? I think it's easier than this. So now we're going to talk about absolute extrema. And candidates just means it's kind of like what we called the critical points. In fact, those are some of the candidates, but those were candidates for local extrema. Now we're just going to use them for this too, okay? So basically what we're adding, if you just draw some random function, it doesn't have to look like this, but we have critical points where we could have these things. Extrema, I mean. But we also now have to look at the endpoints as well. And where are we going to find our endpoints? Like where are they going to come from? Yeah, if we're just given a raw function, the domain, but that could be infinite, right? So what we're going to have to do on this is on an interval. So this will always give us our endpoints, the x coordinates, okay? So what do you think? If I said, what are, like if you read this first question, find the absolute maximum value and absolute minimum value. So remember now we're looking at y. So what do you think we'll do? I bet you could tell me exactly what we'll do in this whole section.
$5 in max, plug in points.
There. Yep.
That's great.
Just find your x coordinates of your critical points. We'll be given the endpoint x's and just see which one's greatest, okay? And that's actually probably in most cases faster than doing the sign table, I think. I don't know for how you feel, but. So let's look at this first one. Actually, let's write this first. So these are going to be your two that we just said. So critical point, the x values, and endpoints, x values. Yay, an easy derivative. Alright, so f prime is what? Yep. Okay, so first we need to find our critical points. Let's just call it CPs. Does f prime of x ever not exist? So f prime always exists, or exists everywhere, we could say, on the interval. Okay, where does x equal 0? Well, we just factor this.
Yeah.
So at 0 and at 2. Okay. So now what do we do? You kind of said it. Specifically, what do we do here? Yep, and endpoints. Where do we plug it in? Yeah, to f. So we'll do f of, let's do it in order. F of -1/2. F of 0, I think, was next. Yep. F of 2, F of 4. Do we need a value or just a sign? Yeah. Okay. So -1/2 cubed is -1/8. -1/2 squared is a fourth. So this is -1/8 minus 3/4. I'll just write that as eighths actually. What is that? 6/8. Okay, and then plus 1 plus 8/8. So that's an eighth. Okay, 0 is easy, that's just 1. 2, so 8. And then minus 12 is -4. Plus 1, that's -3. 4 cubed is 64. Minus 48 is 16, so that's 17. Okay. So what do we know? Yeah. So we can just say absolute maximum of 17 at x equals 4. And you do need, on these, you do need to show your all the value checks so that you have that justification. See, do you guys, it kind of feels easier to me. Those, I don't like those tables, those sign tables. For some reason, they make me second guess and stuff. I don't know. I just get kind of neurotic about it. Any questions on that? Okay, this is kind of weird, this part. So let's kind of talk through it. We have about 10 minutes, looks like. Okay. So if this is a graph of f prime. We can identify relative extrema at the x-intercepts. Why there? Yeah, right? So something's changing from positive to negative or vice versa. All right, so can we find the x-coordinate of the absolutes from this graph? Okay, so where are we thinking we'll check, first of all?
3.
Okay. So maybe we'll just talk through those points. What about this end point? Could it represent an absolute? It could.
Oh, because it could be the endpoint.
Yeah, like, if it's like something like that, right? Okay? So we do need to check that. Why am I going Anyway, the check is what's weird. So we know where to look, but the check is weird. And it's kind of previewing where we're going to go in Unit 6, which is starting to be the antiderivative, which is brief version when we start using it, not just the procedure of taking an antiderivative, but when we start using it in context like this. It's finding areas between curves curves in this case meaning our graph, but also the x-axis. So finding areas like that, finding total lengths, so totals of change. Okay, so if we call that positive, and obviously this is negative, here's how we'll think through it. Think about what, again, this is f prime, and let's look at positive 1 first. Think about what has happened before we get to x equals 1. So this tells us that we have accumulated what? In terms of, like, thinking of a graph, when you hit a max or a min, it's growing, right? So the y value is growing if we're increasing if our slope is increasing, or if it's positive, excuse me. So this is a bunch of accumulated positive change, okay? So 1 at x equals 1 is a candidate for an absolute maximum, because we have accumulated all this positive change. So really what we need to check is, have we gone down very far after we get to that point? Like, have we gone down further than we went up? And the answer is no, right? So we can see that there's an absolute max there, because again, all this positive energy, positive change had come right before that happened, okay? What about 3? So this is a lot of negative accumulation. So can we assume that 3 is an absolute minimum?
No, because negative 3 is where you started, and you don't, because you're not gaining, or I guess you're not losing as much as you had at negative 3. So would negative 3 be your absolute minimum? Because that's where you started from. And you're not losing as much as you gained, I guess.
We don't know where,
We don't know what happened before this.
Right.
which means that,
But essentially, from going off of that graph, you have gained that much area, and you're only losing a small percentage of the area. And so that would mean that negative 3 would be your absolute minimum instead of.
Well, I guess you'd have to know how much you're losing to then determine that, right?
Yeah, I mean, this graph is good enough. Like, if we wanted to justify it numerically, yes. But this graph, I mean, we can clearly see, like, this area is bigger than that area, right? And then we also have that purple positive area. I should have highlighted it as well. Here, between that little section of f prime and the x-axis. So, go ahead.
couldn't f of negative 3 like start really negative, which could be more negative than how far we go down at 3.
Yeah.
So we can't.
So, well, that's what I think you were saying, right? That this could have come from or more green, than that green is. So that when we're accumulating all the positive, it can come up above. So let's pause there and say, what about 4? Is 4 anything? No, because we know around it, the negative takes over. Like, there's more green negative than purple positive, so it's definitely not all the way back up as far as this got, right? So now we just have to debate, is there absolute minimum over at negative 3 or more at 3? Do you agree with him that this negative probably doesn't push this value down as far as what could have happened here because of all this positive that happened after it, so to speak? Right?
But I mean, there could be cases where that one is bigger, right? Or that one would
No.
be, or no.
Where what would be?
Like, 3 would be the minimum,
Only if this would be bigger
Yeah,
here.
that's right.
Yeah. So yes, there could be a case, but not with this situation. Does that
well,
make
that's
sense?
yeah, that's what I'm saying. Like, well, I think.
Yeah, like if for some reason this came down in such a way that area was bigger than this purple. Yeah. But just with that smaller green, it's not. So we have it from this. We can tell there's an absolute max at 1 and then at negative 2, and ambiguous, right? It's not like jumping out at you. It's weird. So we will get, this will become more clear as we do more with integrals and antiderivative work. That's kind of the whole after Christmas push. So we finish the course actually, is that we switch from derivatives to those. And it's a huge part of calculus too. All right, this time I have an assignment on AP Classroom. So it's questions kind of like what we saw, like these kind that we started the day with, and others. I mean, it's not just those, but they are all multiple choice.